This is a continuation on a lecture for rational exponents. In this part, we're going to talk about solving radical or rational equations, and I'm only actually going to talk about solving rational or radical equations of the form junk to the 1 over n is equal to junk, where the word junk can be like 3x plus 1 or 5x squared plus x or something like that. And same thing on the right hand side, it could be numbers or whatever you want. But it's all where the exponent is 1 over n. A few prerequisites here. First thing, you have to know exponents intimately. You also have to know the laws of exponents, everything about integer exponents, including negative and zero exponents. You have to know about rational exponents and how to simplify rational exponents. Finally, you have to know how to operate with radicals. It's also useful actually to know how to solve equations, obviously. Specifically, equations involving one variable or equations involving more than one variable. I know that covers pretty much all equations, but there's different tactics for both of those. Let's actually talk about those right now. In reality, there's only two types of equations. You have equations that have one variable or one occurrence of a variable, or that can be rewritten to have one occurrence of a variable. And then you have equations with two or more occurrences of a variable that cannot be combined. So let me show you what I mean by each of these. We'll start with the most basic examples. For example, 3x minus 1 is equal to 16. How many times does the variable x occur here? Just once. So it belongs to this group. How about 3x squared plus x equals 15? That variable x occurs there twice and it can't be combined. In other words, you have an x to the first power and an x to the second power. Two distinct different powers of x. They cannot be combined. They're not like terms. Therefore, they belong in this group. Let's try another one. Let's try 5x minus 4 raised to the second power is equal to 27. In this case, as you can see just by reading this, it has one occurrence of my variable. Therefore, it belongs in this group. Now, some people may argue, wait a second, I could multiply this out, and if I distribute 5x minus 4 times 5x minus 4, I'll get two occurrences of my variable. And you're absolutely correct, you will. But as it's written, there's only one occurrence of the variable here. This next one, we have x times the square root of x minus 4 is equal to 3. This has two different variables. One is to the first power. The other one technically is to the 1/2 power because it's underneath the square root. So two completely different versions of my variable. Now, sometimes it looks a little tricky, like if I had 3x minus 1 is equal to 5x plus 4. Some people may argue that there are two different variables here. But in reality, I can manipulate this equation by subtracting 3x from both sides. And if I did that, I could change it to become negative 1 is equal to 2x plus 4. And now you see that it has been rewritten as an equation with only one variable. For more advanced things like 2 raised to the x power is equal to 17, while we do not know how to solve this yet, at least in this lecture series, it belongs to this group. There's only one version of the variable. How about the absolute value of 3 minus x is equal to 17? Again, only one version of my variable, so it belongs here. And so on and so forth. So the idea is that if you have one version of your variable, or you can combine things to be one version of your variable, it belongs in this first group. Well, what does it mean to belong in this first group versus belonging in the second group? Well, if your equation belongs in this first group, you can solve these using a very nice technique. The technique is called inverse operations, so you solve each of these using inverse operations. And I'll talk more about that in a moment. If your equation belongs in the second group, well, you're kind of out of luck. You have to solve these using special techniques. And these special techniques are things that you learn, like factoring or completing the square, stuff like that, that are very, kind of random techniques to solve equations. In general, you really want to try to use inverse operations if you can, if you have the ability to. So what do I mean by inverse operations? Well, if you take that first example, 3x minus 1 is equal to 16, first of all, we have one occurrence of our variable here. And so I can start by, well, first thing I like to do is clean up both sides. So clean up each side if possible. In this case, we really, on the left-hand side, there's nothing to combine. On the right-hand side, it's just 16, so there's nothing to do. The next thing I generally do is list out the operations that are being performed. I'll call that ops. And I'll list that out down below here. So a question I'll often ask is, what is happening to x? And this is where we're going to decide our inverse operations. So you look at x, really somebody, if they were really nice, they would just tell me that x is 17/3 or whatever it may be. But unfortunately, somebody's not that nice. What they've done is they've hid the value of x from me, and they've done this by using some combination of multiplication, division, addition or subtraction, or roots or powers or anything like that. They just really try to hide the value of x from me. So our job is to trace what they did. So let's follow the order of operations. Start with x itself and follow the order of operations. Now you look for parentheses around it if there are, but there aren't. You look for exponents on it if there are, but there are not. Well, there's an exponent of 1, but nobody cares about that. Now you move on to multiplication, and you ask yourself, did they multiply x by anything? And they did. So the first thing they did is they multiplied x by 3. So now I have 3x, and then I say, okay, well, after they multiplied by 3, what did they do? Did they do any division? No. Did they do any addition? No. Did they do any subtraction? Yes. The next thing they did is they subtracted by 1. My multiplication here looks like a subtraction, but it is multiplication. So now we need to, what I call, untie that knot, which is basically perform those inverse operations. Now when you untie a knot, this is the knot they've tied up the value of x in. When you untie a knot, you always untie starting with the last knot. So the last thing they did, we're going to untie. They subtracted 1. We'll perform the inverse operation, which means the first thing we're going to do is we're going to add 1. That's the opposite of subtracting. And then once I undo that, I'll look at the next thing that they did, and I'll perform the inverse operation. Now, what's the opposite of multiplying by 3? That'd be dividing by 3. And this is my tactic, my game plan here, so that I'm going to add 1, and just remember that you add to both sides. So I get 3x is equal to 17. And then I'll divide both sides by 3. So that I get, well, on the left-hand side, 3 over 3 is 1. And so I get 1x, or in other words, x, is equal to 17/3. This tactic works for almost all equations, well, actually all equations involving one occurrence of your variable. Let's go ahead and take this next example here. Now you notice in this next example there's only one occurrence of my variable. So what I'm going to do is clean up both sides if I can. One thing I'm going to opt to do is to not distribute here, because I know that'll create two versions of my variable. So instead I'll just clean it up slightly by saying, well, the left hand side I'll keep as 5x minus 4 squared. The right hand side I'm going to reduce that radical. That's the square root of 9 times the square root of 3, or in other words 3 root 3. And that's just from a previous course, a prerequisite course. Now we'll start listing out what happened to x. So remember PEMDAS, the order of operations. You look inside parentheses here, and you say, okay, the first thing that happened to x, let's see, any exponents strictly on x itself? No. Any multiplication? Yes, they multiplied by 5. And then remember, we're still in parentheses, so you ask yourself, did they add or subtract? Yes, they did. They subtracted by 4. Well, that takes care of all the work they did on the inside of the parentheses. So then you hop outside the parentheses and you say, oh, yeah. Then after that, they squared. And so we need to undo all this work that they did. So the first thing we're going to undo is their squaring process. Now, how you undo squaring an object is to take a square root. That's the inverse operation. And then the second thing we're going to do is undo their subtraction of 4 by doing the inverse of subtraction, which is addition. And then we're going to undo their multiplication by 5 by doing the inverse, a division by 5. That's our roadmap to solving this problem. So let's go ahead and start by taking the square root of both sides. So when you do that, taking the square root of the left-hand side unlocks the left-hand side. And you apply the square root to the right-hand side. I know a lot of people hate having roots under roots because they think that it looks funny, but it's actually perfectly fine to do that. But just remember, when you take the square root of a square, within an equation here, you have to have that plus or minus business. That's from quadratics. That's a prerequisite. Now we're going to go ahead and add 4 to both sides. So let me go ahead and say plus 4 and plus 4. When you do that, you get 5x is equal to 4 plus or minus the square root of 3 times the square root of 3. And then finally, we tell ourselves we're going to divide both sides by 5. Now often when I do a division of each side, I end up dividing each term by 5, but neither of these terms on the right hand side are divisible by 5, so I'm just going to divide the entire side. So let's see, the fraction on the left hand side, 5 over 5 turns into 1, and we get x is equal to 4 plus or minus the square root of 3 square root of 3 all over 5, and we're done. And that's because of the fact that we had one occurrence of our variable. Now let's see how all of this idea of doing inverse operations will help us in this section or in this lecture. So let's go ahead and solve 4 times the quantity x plus 2 being raised to the 1/5 power is equal to 12. And you ask yourself when you start solving any type of equation, how many versions of my variable do I have? In this case, we only see one version, so this looks like a straightforward, just go ahead and do inverse operations. You can clean up both sides if you can, but the fact is, inside these parentheses, these two things don't add, because they're unlike terms. And also, on the outside of the parenthesis, this 4 is just a 4. There's nothing I can do with it. It's not like it's 4 to the something power. On the right-hand side of the equation, nothing to do there as well. So I'm just going to list out what happens, what has happened to x. Again, follow the order of operations. You want to look inside parentheses first, around x that is, and ask yourself, are there any exponents specifically on x? No, just an exponent of 1, but nobody cares about that. Is there any multiplication or division happening to x? No. Is there any addition or subtraction? Sure, there's an addition by 2. Okay, great. Now that we've done that, there's really nothing else left on the inside of the parenthesis. So we then mention what's happening on the outside of parentheses. Now remember the order of operations. You look for any parentheses or exponents first. And there are exponents. There's an exponent of 1 to the 5th, or I'm sorry, an exponent of 1/5. So we've raised to the 1/5 power. And now after somebody's raised that x plus 2 to the 1/5 power, so we've taken care of exponents, is there any multiplication happening to that side? Yes, they multiplied by 4. And is there any division or addition or subtraction on the side? No, there is not. So let's go ahead and list out how to undo these steps. Remember, that's like tying a knot, so we always untie the last thing they did. We're going to divide both sides by 4. That's the inverse of multiplying both sides by 4. Then we're going to undo they're raising to the 1/5 power. Now the way you undo raising to the 1/5 power is you want to turn that exponent into a 1. And we'll see, I'll just show you that it's going to be true. We're going to raise it to the 5th power. And we'll see why that works in a moment. Finally, we go to the first thing they did and undo that. So we're going to subtract 2 from both sides after that. So like I said, the first step, divide both sides by 4. And when you do that, well, on the left-hand side, 4 over 4 turns into 1, so that's nicely canceled. So you just get this beautiful x plus 2 raised to the 1/5 power equals 3. And now, like I said, this second step is the one that's questionable to most students. They're not 100% sure why it's true. So I have to unlock this x plus 2 from this 1/5 power. Let's see what would happen if we raised this side to the 5th power. Of course, whatever you do to one side in an equation, you have to do to the other side. So I have to raise the other side to the 5th power. But let's see why this works out. Powers to powers, they multiply, right? So 1/5 to the 5th, right? You have 1/5 power to the 5th power. Those two will multiply. So the left-hand side here will turn into a quantity of x plus 2 to the 1/5 times 5. The right-hand side is 3 to the 5th. 3 to the 5th, I think, is 243. I'm almost positive. Let me just write that out. 3 to the 5th is 3 squared times 3 squared times 3, which is 9 times 9 times 3, or 81 times 3, which is 243. Okay. Now, if you look at this, 5 times 1/5, well, that's 1. So this left-hand side is just x plus 2 to the first power, or in other words, x plus 2. So whenever you see a power of 1 over a number, to undo that, you raise it to the 5th, or to the denominator's power to cancel it out. You're essentially just trying to find the reciprocal of this number and raise it to that power. Well, the last step we tell ourselves to do here is subtract 2 from both sides, so I'll go ahead and do that right now. And that will imply that x is equal to 241. That's our answer, 241. Now, it's probably a good idea to check that, but the fact is I know that's going to be true. So this idea of performing the inverse operation is extremely helpful in this case, and in fact, all cases where you have one version of your variable. Let's try another one here. First thing I'm going to do is notice that there's only one version of my variable. So this tells me I can perform inverse operations. And I'm going to go ahead and try to clean up both sides, but there's really nothing to clean up here. 1/2 is just 1/2. There's nothing to clean up there. 2x minus 3 will not combine. So I'm pretty much done trying to clean up both sides. I'm just going to list out what happened to x. Following the order of operations, first thing that happens to x is it gets multiplied by 2. Second thing that happens to x is it gets subtracted by 3. Now we have 2x minus 3. So the third thing that happens to that 2x minus 3 now is it gets raised to the negative 1/4 power. A lot of students will want to just rip off the negative, drop that downstairs, but trust me, it's much easier just to let that be, and we can undo that in a single step in a moment. So here we go. We're going to go ahead and write out how to undo all this. The first thing we're going to do to undo is take care of the last thing they did. They raised to the negative 1/4 power. We're going to go ahead and raise to the reciprocal of a negative 1/4, which would be a negative 4 over 1 power. After we're done doing that, instead of subtracting 3, we're going to do the inverse of that, which is adding by 3. And then we're going to undo their multiplication by 2 by doing the inverse of multiplication, which is division by 2. So let's see what happens here. I'm going to go ahead and grab this left-hand side and raise it to the negative 4 over 1 power, or in other words, negative 4th power. Same thing with this right-hand side. And you'll see powers to powers, they multiply, so it becomes negative times negative is positive. We'll have a 4 over 4, which will be 1. So the left-hand side just becomes 2x minus 3 to the first, or in other words, 2x minus 3. The right-hand side is 1/2 to the negative fourth power, and now I'm going to go ahead and rip off the negative and flip that fraction. And remember, this is, in mathematics, you're using every tool you've learned. And we've learned that we can rip off negatives off exponents. It takes the reciprocal of the fraction that the exponent is touching. And now I'll raise that 2 to the fourth power to get that. That is going to be 16. So this is 2x minus 3 is equal to 16. And now I just continue following my steps here. I told myself I'm going to add 3 to both sides, so I go ahead and do that. And that gives me 2x is equal to 19. And finally, I tell myself to divide by 2. So I'll go ahead and do that here. Remember, 2 over 2 is just 1, so that's going to be a single x there. And we get a single x is equal to 19/2. There we have it. That's a great tactic. Notice that it avoids a lot of, whoa, what do I do? I mean, this is such a nice algorithm, I guess you could say, to solving equations. But now we're presented with a completely different style of problem. If you take a look at this, there's actually 2 different versions of x here. One's a squared version, one's a single powered version. And so this idea of inverse operations is not super helpful. It does help a little bit. One thing that I'd like, one of the more annoying parts of this problem, is that all of my variables are underneath a cubed root. Now remember, a cubed root is the same thing as saying, oh, I have 2x squared minus 15x raised to the 1/3 power. So at least I can unlock that power by raising both sides to the 3rd power. So I'll do that right now. Raise both sides to the 3rd power. And I get, well, the left-hand side unlocks, so it's just 2x squared minus 15x. The right-hand side becomes 125. At this point, I can't do inverse operations like I have been doing, because the fact is there's 2 different versions of my variable. So when you are faced with that situation, you have to resort to special techniques. The special techniques here are some way to solve a quadratic equation. And whenever you're trying to solve a quadratic equation with 2 or more versions of your variable, you end up having to move everything to one side. So let me go ahead and subtract 125 from both sides to get all my non-zero terms to one side. So this will be 2x squared minus 15x minus 125 is equal to 0. And I'm going to first try to solve this using factoring. I'll take a look at this and go, okay, I want to make sure that I can't factor anything out of all 3 terms. I look through all 3 terms, there's nothing in common. And then I start thinking, okay, 2 numbers that multiply to 2 are 2 and 1. And 2 numbers that multiply to 125 are 5 and 25, or 1 and 125. Those are my choices. Those are how those will split. So let's see how this works. We have a 2x, hopefully, and a 1x. And then to create that last term of 125, we either are going to try 5 and 25, 25 and 5, 1 and 125, or 125 and 1. And then we just basically do this thing, 2 times 25 and 1 times 5. So 2 times 25 is 50, 1 times 5 is 5, so we have 50 and 5. Is there any way for 50 and 5 to be added or subtracted from one another to get to a negative 15? And the answer is no. So we'll cross that out. That's not a possibility. And then we take a look at the next one. 2 times 5, 25 times 1, that's 10 and 25. Is there any way to combine 10 and 25 to become a negative 15? The answer is actually yes. we can combine 10 and 25 to become a negative 15. So I'm going to go ahead and write these up above here. If I want to become a negative 15, I need it to be a negative 25 and a positive 10. Now just double check our work here. 2x times 1x gives me a 2x squared, so that's that bit right there. 2x times 5 is 10x, minus 25x is a negative 15x. And finally, negative 25 times 5 is a negative 125. So this is our factorization. Now at this step, we're going to go ahead and find the solutions. I have two objects multiplying to become 0, means that either the first one is 0, or the second one is 0. So if I solve this first one, I'll get x is equal to 25 halves. If I solve the second one, I get x is equal to a negative 5. Now something that I didn't mention before, that I should mention at this point. You need to always check your work when you're solving these problems. The reason why is that when you square a side or cube a side or raise a side to the fourth power or anything like that, you run the risk of introducing what are called extraneous solutions. So I even wrote it as a note here: when solving a rational exponent or radical equation, always check your solutions, especially when you're doing any type of raising to a second power to get to a solution, or to the fourth power or to the sixth power. Basically raising to even powers, you run the risk of introducing incorrect solutions, what we call extraneous solutions. And I'll talk more about this in a lecture dedicated to rational equations or radical equations, but it's just something that you should get in a good habit of doing, and realizing that, in this case, this example right here, when we solved, we raised both sides to the third power. Technically, there's no risk of introducing a wrong solution here. And actually, in this example right here, we raised both sides to an even power. Even though it's a negative even power, it's still considered an even power. So we run the risk in this case of actually getting a wrong answer, just because we're raising to the fourth power. It turns out, well, let me explain why. What if we got to a solution that was, let's say, a negative 19 halves? Even though it's not a negative 19 halves, let's just pretend for a moment that we got to a solution that said x is equal to a negative 19 halves. Had we not checked that, well, it wouldn't have been, we would have thought we were right. But the fact is, the original equation, which is 2x minus 3 to the negative 1/4 is equal to 1/2, could have been rewritten as, well, let me rip off the negative and drop that downstairs. That could have been written as the fourth root of 2x minus 3 is equal to 1/2. And if the x in here was really negative, like negative 19 halves, then we'd be taking the fourth root of a negative number. And you can't take the fourth root of a negative number. So you see, the issue is that when you're solving, because you're taking out the fourth root, in this step right here, there's no longer a fourth root on that 2x minus 3. You now introduce the ability to get negative solutions, very negative solutions. So you always have to check your answers. Just because a solution is negative doesn't mean it's wrong. It's if, when you plug it into the original equation, if your radicand turns into a negative, then that solution would have been extraneous. It's not an issue right now because I'm not really going to focus on that. So none of these examples have that issue. But it's just a warning for future reference. As a final example, I'm going to do an application problem. Membership in the county museum has been increasing slowly since it was built in 1950. The number of members is given by the function m of t is equal to 72 plus 100 t to the 1/3, where t is the number of years since 1950. Now part A has two parts to it, really. How many members were there in 1960 and in 1970? These type of problems I really dig, because the fact is that you have to be aware of quite a few things going on. T is the number of years since 1950, so 1960 corresponds to t equals 10, because that's 10 years since 1950. 1970 corresponds to t equals 20. So for part A, we just want to know what is the value of the function m when it's evaluated at 10 and then at 20. Let's go ahead and do this. 72 plus 100 times 10 to the 1/3. And in this case, the third root of 10 is not something that I know offhand. So I get to use a graphing calculator here. And I'll go ahead and just type this in. 72 plus 100 times, and then we'll say 10 and raised to, now remember it's the 1/3 power, so I'm just going to, whenever you have a complex exponent like that, you want to start with a parentheses, so parentheses 1/3 power. So I'm raising 10 to the total of 1/3. 287, that's the membership. Usually with a problem like this, it's that you want to round down because you're talking people and you can't have 0.4 people. So 287 people were members in 1960. In 1970, again, the same tactic here. I'm just going to plug in 20 because it's 20 years since 1950. A little fast note about your graphing calculator if you have one. Second and then entry will bring back your last thing you typed in there. I can just replace that with a 2 instead of a 10. 343. Nice. So it has been rising steadily. Part B, in which year did the museum have 400 members, is basically asking me, when is the number of members? When is the output 400? So we want to solve something like 400 is equal to 72 plus 100 t to the 1/3. Notice this equation that we're going to be solving here has only one version of our variable. So if you think about what's happening to t, well, I'm going to quickly write off to the side. The first thing that happens to t is that it gets raised to the 1/3 power. The second thing that happens to t after it gets raised to 1/3 power is that person multiplied it by 100, whoever that person is. And then finally they added 72 to that result. So we're going to undo that. I'm not going to list out the undo steps. I'm just going to say them as we do them. So we're going to untie that addition of 72 by subtracting 72 from both sides. And when you do that, let's see, 400 minus 72 is 328, I think. So we get 328 is equal to 100 t to the 1/3. Now I'll divide both sides by 100 because to undo the multiplication of 100, we do a division of 100. So if I divide this side by 100, I have to divide the other side by 100. You'll get 3.28 is equal to t to the 1/3. And finally, to undo the 1/3 power, I'm going to raise both sides to the 3rd power. So raise both sides to the 3rd power, the reciprocal of 1/3. Now this I have to grab a calculator for because this is, and I'll even say roughly equals to. I have to grab a calculator for this because the fact is this is not a number that's fun for me to raise to a power. So 3.28 raised to the 3rd power, I get 35.28, or actually 0.29. We'll round nearest tenth. So 35.3. Now, what does that mean? Well, this is asking me what year did we have 400 members. That'd be 35 years after 1950. So that'd be 85. So in 1985, there were 400 members. Okay, so let's go ahead and move on to the, well, The second part of part B, I'm just going to let you know, it's the same thing, right? If membership continues to grow according to the given function, when will we have 500 members? You would change this 400 to a 500 and do the same thing. It'd just be a later date. The part that I'm really interested in doing here is graph the function m of t, and how would you describe the growth of the membership over time? Now, graphing this function is very important because the fact is that we have spent time graphing functions in the past. So let's do that here. So I've drawn a set of axes. You have a t-axis, you have an m-axis for the number of members. T is the number of years since. So years since 1950. Okay. And one thing to note is that I'm going to go ahead and use base transformations. So base graph transformations. Now, a lot of people will use a graphing calculator here, and your instructor might be fine with that. That's totally okay with me. But I'm going to actually go ahead and just get an idea of what this looks like using base graphs and transformations. The base graph for t to the 1/3 is the cubed root of t. And the cubed root graph, if you remember, looks like this, sort of. Okay. And I usually write this out, by the way, as 100 times the cubed root of t plus 72. It's a little bit easier for me to see like that. And I'll read from left to right. So from left to right, 100, recall, a number on the outside of our function, multiplying the outside of the function, stretches the function. So that's a vertical stretch. Vertical stretch. That stretches all the y values by a factor of 100. So in reality, it's very difficult to draw it on the same set of axes. It'll look something like this, my guess. Something like that. Okay? I mean, really, when you're doing a base graph, you're just trying to get a basic idea of what the graph looks like. And if you look back at this question, graph the function, how would you describe the growth of the membership over time? The only reason to use base graphs is to get a basic idea of what the graph looks like. The plus 72 means grab this anchor point here and lift it up 72 units. So you might have something that ends up looking like this. So this is going to be at t equals 0, m equals 72. It's increasing very quickly and then kind of leveling off, something like that. So if I look at that, I'll just draw it in here and again, say it looks something like this. Oops, I incorrectly graphed that. Sorry about that. I'll say that's a height of 72, and now do this. 0,72. And it's nice probably to throw in a point other than 0,72. So you could take a point that, choose a time value that you can take the cube root of easily. For example, 1. If you choose a value of 1, then you'll have the point 1, comma, well, let's see, cube root of 1 is 1, times 100 is 100, plus 72 is 172. There we go. Now, obviously, this is not to scale. It should really be up higher, but this gives me a basic idea of what's happening. The question is really saying, describe what happens to the membership as time goes on. Well, the membership looks like it's increasing slowly. I mean, not slowly. Initially, it increases quickly, but then it slows down over time. So it's always increasing. That's the first thing I'd probably mention to anybody who's asking, maybe a business partner or somebody who wants to invest here. I say, listen, membership will always increase, but as time goes on, it just doesn't increase as quickly. Now, I would like to verify this graph on my graphing calculator just to convince you that it actually is true. I'll hit y equals here, clear out any old graphs I have in here, and I'll type in 100 times x, so times x You don't have to. You don't want to use t because your calculator won't understand that. Raised to the 1/3 power, and then plus 72. Now, if I hit graph, I'm not going to see anything. The reason why is because my window here, well, I only see a little bit. My window goes from a -10 to a +10 in both x and y. So I'm going to have to adjust my window. And I'm going to go ahead and go from x equals 0 to x equals 10. That's fine with me. And I'll go from y equals 0 to y equals, let's do 2, well, actually let's do 600. So you see what happens, it's always increasing, it just increases slower and slower as time goes on. And in fact, had I adjusted my window to be from -10 to 10, maybe in the, oops, I meant that to be also in the y direction. So let me change my window in the y direction as well. We'll go from a -300 to a +300. Sometimes you have to kind of wiggle with these things a little bit until you get a graph that you like. There we go. So notice it does really look like our graph, right? There's a quick steep increase, then it kind of levels out. Not really levels out though. It always is increasing. It's just not as quickly as it was initially. So my only advice to you on a problem like this, other than you should be able to do all the stuff that we've mentioned, is that when you're graphing a function like this, you're really only graphing it to get a basic description of what does it look like as time moves on. Use base graphs and transformations. If you need to review that, I do have a lecture on base graphs and transformations of functions and stuff like that, so please review that lecture.